This is done using backward reasoning. So you go from the so you go back to solve all the small problems that arise in creating those pieces together. So that is done through backward reasoning. So this is basically how we get basically a mixture of both the reasoning approaches. So if you consider in terms of basically your operators or basically a more formal kind of an algorithm, so let us see that. So in a more formal way, we write it like this, that you have a current state and you have a goal state, right? So you want to find out, basically you want to reach the goal state from your current state, correct? So what you do is you estimate that how much difference is there from the current state to the goal state, right? And then you find out some way how you can reduce this difference. So you want to reach the goal state, so eventually you will have to reduce this difference, right? So how to reduce this difference? You find some operator that can be applied, but actually sometimes it may not be possible that whatever operator that you are applying, that is directly applicable to the current state. Fine. So that can also happen sometimes, that the operator that you are applying is not directly applicable to the current state because its preconditions for applying that operator are not satisfied by the current state. So in that case, what you do is, so in that case, you cannot apply the operator directly to the current state. So what you do is you basically find out a sub-goal state or another state in which that operator can be applied. Okay, so basically we find out another state from this current state, which is basically another sub goal where that operator can be applied and all its preconditions are also satisfied. So basically, this is some other state which you have generated from the current state. So it's generated through backward chaining. So what you do is, if your current state is not the state where you can apply that particular operator, so you select the operator and where you want to apply that operator. Now that operator is not applicable to the current state. So what you do is you basically select some particular state in which that operator's preconditions are satisfied and can be applied. So you have selected an operator, but it's not applicable for the current state. So you generate the state in which it is applicable. And then you apply that operator. Now, when you apply that operator, so after you apply that operator, it may not be possible that directly you have reached the goal state, right? So you may apply that operator and it may not be possible that always you reach the goal state from that operator. So basically, you may not get the exact goal state, but you will be nearer to your goal state, right? So you may not get the exact goal state, but you will be somewhat nearer to your goal state. So what you do is you have another sub-problem of getting to the exact goal state from the state that this operator has generated, right? So basically there are two things over here. When you apply the operator, it may not be applicable exactly to the current state. So you will have to apply it to some other state. Basically you have to generate some other state from the current state in which that operator is applicable. Then when you apply that operator, you will not be able to generate exactly the goal state. You will be generating an intermediate state. Now the another sub problem is for going from that intermediate state to the goal state. So basically when you apply an operator, basically after application of an operator, you will be able to basically bridge some gap between the current state and the goal state, but not all the gap, right? So basically you will be able to minimize the difference between the current state and the goal state, but not completely by the application of just one operator, right? So when you apply one operator, you will be minimizing some difference from current state and goal state, but actually it will eventually lead to two more differences which you have to minimize. Those two differences would be from the current state to that state in which you have applied the operator, and the other difference would be from the intermediate goal state which you have reached to the exact goal. So these two differences also you will have to minimize after applying that operator. So this way you have to go on, and when you are able to minimize all the differences between the current state and the goal state, then you have reached the goal state basically. So this is what is the gist of this algorithm. It is written here also. Whatever I just explained you, this is also written over here. So what we are doing is you are comparing your current to the goal state. So if there is no difference, that means you are already on the goal state. So you return. Otherwise, you select the difference which is most important for you to minimize. Right. So basically, there could be from the current state to goal state, there could be many operators possible. Right. So you have to choose which operator will minimize the difference to the maximum, and you have to select that operator again which will minimize the difference to the maximum possible. So you select that operator and apply the difference, right? If there is no operator available which can minimize the difference, then obviously your algorithm will fail because it requires an operator to minimize the difference eventually. So you have to get an operator. So now you select an operator which will be able to minimize the difference to the maximum. And then this operator, which can minimize the difference between the current state and the goal state, this operator may not be applicable exactly to your current state, as I said earlier. It may not be always possible that this operator is able to minimize your difference. I mean, in one operator application only, you will be able to get the goal state. It is not possible. And also, it is not possible that that operator would be applicable exactly to your current state. So basically, in order to apply that operator to the current state, you have to generate another state basically. So that is, let us say we are calling that state as O start. So O start is a state in which operator can be applied and all its preconditions are satisfied. So this is a state which you are generating from the current state in order to apply that operator O. So O start is a state in which you are applying the operator O. And then O result is a state that is the resultant state after you are applying that operator O to O start. So you get O result. So basically, you have minimized the maximum difference possible. Difference that you have minimized is what? The difference that you have minimized is from O start to O result, right? That is the difference which you have minimized. But still, what is remaining? What differences are remaining now? See, you have not applied the operator on the current state. You have applied to O start and you have not generated the goal state. You have generated O result. So basically you were able to get from O start O result. So we generally say that you were able to minimize the difference between O start and O result. But what about the remaining differences which you have created? So what differences you have created? So from the current state to the state O start, that difference you have created, right? Another difference which you have created is from O result to the exact goal state, goal. So basically two more differences have been generated after this application of the operator. So you have to minimize those two differences also. So how? You will again apply means ends analysis algorithm to those two differences which you have created. So how you will apply? You will just recursively call this means ends analysis algorithm with the states as current and O start. So now from current you have to reach O start. So you'll apply the means ends analysis algorithm again. So that algorithm will again select the operator which will be able to minimize the maximum difference possible. And then it will be able to apply it to the current. If not current, then again you have to generate some state from current and apply it to there. And if it is not generating O start, then you have to get an intermediate goal state, and from that again you will reach the O start. So like this, you have to go for the second part also for O result and goal. So when you apply means ends analysis to O result and goal, again you have to find out an operator which can minimize the difference. If no such operator exists, then you have to select the operator which will be applied to a some intermediate state from O result. And it will also be generating goal or an intermediate goal that is also dependent upon the operator selected. So you will recursively proceed with minimizing these two differences, and finally you will concatenate the result of the first part with the operator O which you had applied initially and the second part. So first part is from current to O start, then you have the operator which will be from O start to O result, and then the second part is from O result to goal. So finally when you concatenate all this, you will get the solution from current to goal. So that is how you have minimized the difference from current to goal. Are you able to understand this, students? The theoretical part. We will take an example also. But is it clear? Are you able to get an idea? Okay, what about others? Nitin has only responded. What about others? Okay. Students, if you don't understand anything, then please let me know. Stop me in between and ask. Okay? All of you. This is for all of you students, not only for some students who are interacting in the class. This is for all of you. If you are not able to understand anything or confused in anything, then please ask me to repeat. Okay? Fine. So let's move then towards an example of means ends analysis. So this example is basically a robot example. It's a household robot, and we basically we have given the robot a task. So the task that we have given to the robot is that there is a table on which some two things are kept, and we have to move this desk, or you can say the table, from one position to another, basically from one room to another. And the task, basically we have to move the robot has to move the table from one position to another, and it has got two things on it. So first of all, the two things, basically the objects on it must also be moved, so those two things also should be moved. But actually when you are moving the table should be clear. So you have to first of all remove those two things from the table, then push that table towards the other position, and then again keep those things on the table. So your table will move from one position to another, and it will be basically not having those two things. So first of all, you have to remove those two things, then you have to move the table, and then finally you have to place those two things on the table again. This is the task which we have given to the robot. Now, in order to solve this task, let us see certain operators and what all task, which operators can perform which task. Let us see this thing. So see students here, we want to move the robot. Let us say we want to move the robot. So that can be accomplished by an operator which we call as walk operator. So walking operator will move the robot. And what is the precondition of the walking operator? Just see this table, students. So precondition is none, because you don't need anything to walk. You don't need a precondition to walk. So operator is walk, and it is taking a location as an argument. So basically in whatever location it is, it wants to reach that particular location, right? So it's taking a location as an argument, and the result is robot is at the location. So at robot comma location means robot is at the location. So walking towards the location specified by this LOC location. This is the walk operator. So if you want to move the robot, you will basically use the walk operator, right? So move the robot means walk operator. Then, then which other operators can you apply for which particular task? This table actually describes that, right? So if you want to basically move an object, right? So you can use the push and carry operators both. So let us see what are the push and carry operators. See, you want to move an object. So that object can be the table also, and that object can be the thing on the table. That is the thing which is kept on the table also, right? So if you want to push a particular, let us say you want to push table in this case, if you basically, when you want to move an object, it means you are pushing a heavy object, right? So let us say in this case, a heavy object as a table, and carrying means the lighter object, so it can be the thing on the table, right? So if you are moving an object, you can use both these operators. So if it's a heavy object, you will use push. If it's a light object, you will use the carry operator, right? So now let us consider the push operator. So for the push operator, you will require an object which you are pushing, and the robot should be at the object. So that object is basically the table over here, right? So the table is basically your object. So robot is at the table and the table is clear. There is nothing on the table. This is a precondition for this operator. So if you want to push the table, it should not be having anything kept on that table. So this is a precondition for applying this operator. That is why it is written at robot comma object intersection with clear object. Clear object means there is nothing on the table. Object is the table. So clear object means nothing is on the table. Right. So, so when robot is at the table and nothing is on the table, so preconditions are satisfied. So then when you apply the push operator, it will result in what? It will basically result in that you have pushed the table to a particular location, right? So the object will also be at the location. That means table has reached the location and robot will also be at the location. So table as well as robot both will be at the particular location after pushing. So this will be the result of push. Right now, this is about push. Now, if you see for carry, so carry operator is basically your robot is at the object because it wants to carry that object. So robot is at the object. So this is a precondition for carry, but there is no such precondition that you have to clear the object because it's a thing kept on the table. It's a lighter object. So it's basically you have to carry that one. So the literal meaning of the word carry is also picking up. Basically, it's you're holding that particular thing in your hand, right? So basically you are not having a table in your hand. You cannot have a table in your hand. Basically, it's a lighter object only always. When you are carrying, it's a lighter object. So you don't have a precondition that the table should be clear in the case of carry operator, right? So now the carry operator also takes as arguments the object which you want to carry and where you want to carry, that location also it wants. So it takes two arguments, object and location. Similarly for push also it was taking object and location as the operators. Right. So when we apply this operator, then the object is basically carried to a particular location. So your result would be the object is also at the location and robot is carrying the object. So robot will also be at the particular location. So this is results for push and carry. So now we can say that move object is basically accomplished through both the operators. If you want to move the table, you will use push. If you want to move the book on the table or anything on the table, you will use the carry operator. So basically for moving an object, you can use both these operators, push and carry, right? For moving the robot, you will use the walk operator. And then what all other operators you can use for what all subtasks. So let us say I want to clear the object. Basically, I want to clear the table. So I'll use the pickup operator. Pickup will basically pick up the thing from the table. So let us see what is the pickup operator. See, pickup operator is having an object as an argument. So it's taking an object which it wants to pick up. And precondition is robot should be at the object because otherwise how it will pick up. First of all, it should be at the object. So the robot is at the object, right? So now it picks up that object. What is the result? That it is holding that object. So the result looks like this, holding the object. So it has picked up that object. So now the object is in the hands of the robot. So it's holding the object now. Fine. So basically this is the pickup operator. Fine. So now if you see this table, so clearing the object means you are picking up the object, it is in the hands of the robot, so it is not on the table. So anyways, the table is clear now. Other task which pickup operator can also accomplish is it can hold the object also, right? So basically, if you want to hold the object, then also you will use the pickup operator. Just see in the pickup operator, the result is it is holding the object, right? So even if you want to do this task, if you want to hold an object, again you will use the pickup operator. So basically, the pickup operator is meant for holding the object also and clearing the object from the table also, right? So this operator performs two subtasks, right? Now you see the put down operator. Put down operator is basically used to get the arm empty, robot arm. To make the robot arm empty, we will use the put down operator. So let us see the definition of put down operator. Put down operator is taking an argument as an object and it is holding the object, and the result is it is not holding the object. So precondition is it was holding that object, and now the result is it is not holding that object. Fine. So if you want to make the robot arm empty, you will use this put down operator. So it will put down that object and the robot arm will become empty because it is now not holding that object. Right? So get arm empty, that subtask can be fulfilled by using the put down operator. Fine. And then finally the place operator. So place operator also performs two subtasks. If you want to place an object on an object, you can use a place operator. Otherwise, if you want to place that object on the table, then it will make the robot arm empty. So in order to get the robot arm empty also, you can use the place operator. So just see the definition of place operator. See, place operator takes an object, two objects basically, object one and object two. Now, the robot is at the object two and it is holding the object one. Fine. And the result is the object one is now on the object two. So that's how you have placed the object one on object two. Right. So basically, placing can be on one object on top of the other, or placing can be on the table also. So basically, there are two things on the table. So it can be like this, that you are placing, the robot is placing one book over the other book. That is also called placing. Or otherwise, if the robot is placing one book on the table, that is also called placing. Right? So basically, this object one can be the table. The object two can be the table or some other thing also. So if it is the table, then the book is placed on the table. If the object two is also a book, then the book is placed on another book. Right? So that's how I'm saying that if basically, so that's how I'm saying. If you see this table, so that's how I'm saying that the place operator can serve two purposes. One purpose could be get object on object. So basically, if you are having a book and another book, so it will place the book on another book, right? Or if it can place the book on the table also. So this is get object on object. Otherwise, basically it can make the robot arm also empty, because if you are placing something and it was already there in the robot's arm, so now when you have placed it on the table, it will be, the robot's arm will become empty. So basically these two purposes place operator can serve. So basically, this table which you are seeing, actually students, this is called as a difference table. Difference table means that, so difference table is basically what all subtasks which I am telling, these are nothing but, we generally call them as differences. So this is a terminology that we use in the means ends analysis, that whatever subtasks you are trying to basically execute, those subtasks we call them as differences. So basically we say like that. So I will use the walk operator to minimize the difference move robot. So move robot is my difference or my subtask which I want to perform. So basically, if I want to minimize the difference of move robot, so I'll use the operator walk. If I want to minimize the difference get arm empty, I'll use the operator put down, like this. So these subtasks are basically called as the differences which you are wanted to minimize, and the push, carry, walk, pick up, put down, place, all these are nothing but operators. So this is called as a difference table. Okay, so if you see from this difference table here, one thing to note here is that one operator can also serve one or more subtasks, or it can be used to minimize multiple differences. So this is one observation from this table, that one operator can minimize multiple differences, right? And the other observation is that one difference can be minimized using multiple operators. If you see, move object difference can be minimized using the push operator also and the carry operator also. So basically one difference can be minimized by multiple operators, and one operator like pickup. If you see pickup operator, it can minimize the difference clear object also and beholding object also. So one operator can minimize multiple differences also. So this is basically one observation from this difference table, right? Now you see how we solve the means end analysis problem using robot for this robot example. So basically I want to move the robot, basically I want to move the table from one position to another, right? And it should not have any things on it. So first of all, what will be the major difference in this case, the most important difference which I want to minimize? So the most important difference which I want to minimize in this case would be basically if I use the push operator, that will be the operator which can minimize the difference to the maximum, because the major action involved in this particular task is the movement of the table from one position to another, isn't it? Then the subtask would be that the table is empty, and when you reach the particular destination, your table should have the things on it. But the major task is that you have to move the table, right? So if you want to move the table, or you can say, so basically, which operator you will apply to move the table? Table is an object, right? So the most important difference that you will use, basically the most important difference will be minimized through the push operator, isn't it? So you'll use the push operator to minimize the most important difference. So basically, but one thing over here is that the push operator cannot be applied to the starting state. Starting state is basically the robot is somewhere, right? You don't know where the robot is. It has to first of all reach the table, and then it has to make the table empty. Then only it can push the table, right? So the starting state is the robot is anywhere. We don't know the location of the robot. Fine. So that means the push operator cannot be applied to the starting state. Fine. So you have minimized the most important difference, that is you have reached from B to C, but actually B state is not the starting state. Fine. So you got another two differences to minimize after you minimize this difference from B to C. So what are those two differences which you got to minimize? The difference from A to B and the difference from C to the goal state. Fine. So now from A to B, how you will minimize? So A is your starting state, and you have to reach a state where your robot is at the table and the table is empty. So how you will minimize that difference? So first of all, the robot has to walk towards the table. So using the walk operator. So you have to move the robot. So that means through the walk operator, right? So you move the robot using the walk operator. So you apply the walk operator. Now the robot is at the table. Fine. But the robot is at the table, but the table is not empty. So again, you have not reached the B point, right? So in order to reach the B state, you have to make the table empty. So which operators you will basically apply to make the table empty? There are two things on the table, right? So there are two things on the table. You have to remove both the things, and those two things the robot might not be able to remove at one go, because those two things might be at different places on the table, right? So if the robot is picking one thing, then its arm is not empty. So first of all, it has to put down that one thing. Then another thing it has to pick up, and then it has to put down, right? Because if it has picked up one thing, its arm is not empty. So it cannot pick up another thing, right? So they are at two different places. They might be at two different places on the table. So robot has to use two pickup operators. First pickup operator will pick up the first thing, and then it has to put down that thing. Then the second pickup operator will pick up the second thing, and then it will put down that thing. So what is you are asking, Nitin? If it picks up and doesn't work, then it would put it back on the same place. Yes, yes. So basically, it has already worked, right? If you see from A, first operator we have applied is walking only. So if it has walked towards the table. So after this step, it is at the table position. Now it is picking up the things from the table. If it doesn't work, then it is not reached to those things also. So how it will pick up? There is nothing on its current position. The things are on the table. So it has to reach the table first of all. Right? If it doesn't work, then basically walking is first to reach those things. So that thing doesn't apply over here, because it has to pick up first.
Ma'am,
Right? Yeah.
I was asking, after it walked and picked up the object,
If it
then it is, ma'am, after it walked and picked up the object,
huh?
then it is at the
So
same position of the table.
okay.
Then when it will put down, it will put it back on the same place from where it has picked up. So there
Yes,
is
yes,
no
yes, yes,
global
yes.
movement.
Yeah, yeah, that it will do at the same place only. If it has picked up from the same place and you ask it to put down, it will put up it. Uh, what you are asking, am I not getting your question correctly, Nitin? So according to my,
Ma'am,
yeah,
there should be a work operator also between pick up and put down.
why?
Ma'am, because first it will pick up, then it will put it down on somewhere else. Otherwise, if there is no work operation, it will put it down back on the same position.
No, 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 it's not like that. Pick up is pick up from the table. Put down is put down on the ground. Okay. So
Okay, ma'am.
basically, it's picking up from the table and holding it and then putting down on the ground. Basically, it's like that.
Okay.
Okay. Fine. Fine. So at same place but on the ground, like or not on the table. It put down means down. Down means on the ground. Okay. So it means like this. So in this example, so basically picking up put down means it has cleared one object from the table. Now another pick up and put down will put down the other object from the table. Right? So now the table is clear. So now you have the C state. Fine. So now it will push the table towards the destination point. So it has reached the C state. This is not the goal state right now also. Right? This is not the goal state because table has reached the destination, but again the thing are not placed on the table. So what it has to do, it has to basically put those things back on the table. So what the robot will do, it will walk to the previous point where it has placed those things. So it will just walk to that point, so using the walk operator, and then it will pick up those things, right? So here it will pick up both the things and will carry them. Pick up means it will be holding both the things and then it will carry using the carry operator. It will carry. So the robot was at the object and then it is carrying. So the result is the object is also at the location and robot is also at the location. So it has reached the table location now. So it has reached the table location. So it will use the place operator to place it on the table. Why place operator and why not put down operator? Because place operator is used to place the one object over the other. So that object could be a table and the other object are both the things. So it is placing both the things on the table. Finally, when it has placed both the things on the table, it has reached the goal state D. So that's how. So this is one important thing here, students, that walk the for minimizing the difference between C state and D state, we are using four operations: walk, pick up, carry, and place. Fine. So this is basically you are picking up both the things, carrying both the things, and then placing both the things on the table. That is happening over here, right? So when you are carrying, you can carry n number of things. It doesn't matter. Fine. But when you were initially making the table ready, at that time you were using two pickup operations to pick up both the things from different places on the table, and you were placing it on the ground. So one thing was there when you were using the pickup operation over here, that the you were using two pickup operators, right? So the logic was that basically when the robot picks up one thing, then the robot arm is not empty. It is now holding that object, right? So another pickup cannot happen unless the robot arm is empty. So it has to put down first that object. Then another pickup. So that is why for two objects, two point. But when it is picking up in the second, I mean in the C2D states, from the C2D states when you are trying to minimize the difference. So at that time when it is picking up, so it's basically picking up both the objects and directly placing them on the table. So it can basically pick up both the objects at one go and place it on the table. It can carry them and finally place it on the table. Is it okay, students? Are you able to understand how we minimize the difference from A to B and from C to D? Are you able to get all of you? Please respond, students. Are you listening to me? Yeah, so basically, one thing what I was saying is it's picking up two items with the one pickup operator. Actually, there is no restriction how many items it can pick up. It can pick up two items. So it can pick up any number of items. There is no restriction like that. That object could be pile of books, right? So if there are, because both of them are placed, basically both of them are placed at the same position, right? When you are placing them on the same position, it can pick up both of them together also. So picking up means it can pick up a pile of books together also, right? But when you are picking up from the table, at that time you were using two pickup operators because it's placed on the table at two different points. So basically, when you hold one object, you cannot hold another object unless the arm of the robot is empty. So at that time, you need to put down the first object, then you can pick up the second object. But in the second case from C to D, in the second case from C to D, when you are trying to minimize the difference, at that time this is a pile of books basically. The two books are kept one on the top of other, so you have the robot has picked up as a pile, and then it is carrying the pile together. Normally, right? So some normally, if you see a household example, some things are kept on the table, so you will pick up one at a time, right? And you are placing them on a pile. Fine. So you have created a pile of books. Now you can take the pile together in one go only. So that is why when you are taking that pile, you can take it in one go only. But when you are removing from the table, at that time you require pick up, put down, and you are putting down on the same place. All of them. Like a normal common household example, like we do in our daily lives. Are you getting Abhishek? This is a normal common example of normally how do we do. Yeah, in this case, it is putting down on one on top of the other so that it creates a pile of books. Then it is basically picking up the pile of books together and carrying them together. Okay. No, no. Table means it is, see, the robot's hand is this much large. If the table, it can reach the table. It doesn't need to walk. The table is basically a normal table only. So if it is something is kept on the table, do you need to walk? You generally, the table is accessible by the hand. It is assumed that the table can be accessible by one hand reach. Okay, fine. Okay, so is it okay, students? Mayank, is it okay? Have I answered your question? Fine. Okay, students. So this finishes our heuristic search technique, students. So let us start with another topic today. 1 minute. Let me open another slide. So we have finished heuristic search technique, students, today, and now we'll start with knowledge representation techniques. So knowledge representation is another domain of artificial intelligence. Till now, we have studied how do we find the best solutions, right? So how do we basically, when you represent the knowledge, how should you represent it in an efficient way? That is also one other domain of AI, knowledge representation, and it is a very important domain. So till now, you have done whatever you have done, that heuristic search techniques. That was how you solve the problems intelligently, right? Now, how you represent the solutions intelligently. Fine. This is basically knowledge representation. How do you represent your solutions intelligently or in an efficient manner? Fine. So let us begin with knowledge representation. So basically, as a name tells you, so how do you represent the common knowledge in an understandable format, right? So it should be understandable by the human beings and readable by the computers also. Fine. So how do you represent the knowledge? So generally, if you write any sentence, fine. If you write a sentence which might be a declarative sentence, for example, if I'm writing Lucy is a dog, so basically I'm declaring a fact, right? This is a declarative sentence, right? That Lucy is basically a dog. So fact is what? Fact is a truth. in the real world, right? And the way in which I represent those facts, that is basically the knowledge representation. Fine. So I can represent this fact in terms of certain symbols also. If I represent in terms of certain symbols, that is basically an internal representation of knowledge, right? And if I'm representing it in a normal English language, that is a natural language. So English language is basically a natural language understanding, or you can say a natural language representation. But when I represent it in some internal representation format, like if I can represent it in some logic format, that becomes an internal representation, or you can say a symbolic representation. Fine. For example, if I write Lucy is a dog, this is a natural language sentence, right? But when I declare it like this, when I write it like this, dog bracket Lucy. So this is the representation in mathematical logic. So this is the representation. This is basically a mathematical logic representation. So by mathematical logic representation, what I mean, it's basically, you will study further, it's basically called as predicate logic. So this representation is basically called as predicate logic representation. So what you do in this representation is that your instance of an object, you place it in the brackets, and the object you place it as a predicate. So basically there is a predicate which is indicating your object, fine, and the instance of the object, that is basically the argument of your predicate. Just see the chat box, students. So basically, your object becomes your predicate. That means your object is the dog. So predicate means whatever is coming outside that bracket. That is a predicate. Fine. So that object becomes your predicate, and the instance of the object. Instance of the object means example of the object. So Lucy is an example of dog, basically, right? So that example, or you can say that instance, that comes in brackets. So basically, the format of writing the any sentence in this representation of predicate logic is predicate bracket arguments, and these arguments are nothing but the instance of that object. So predicate can be an object, and arguments can be an instance of objects. So like this, we write dog bracket Lucy. Right. Now, if I write all dogs have tail, this is another fact, right? All dogs have tail. This is another fact which I have declared, right? So how I will write in predicate logic? For all x, dog x implies has tail x. So dog x means dog is the object, and x can be any dog. So x is basically an instance of dog. So if x is a dog, this implies that x has tail. So this holds for all x. So basically, it will eventually represent the sentence all dogs have tail. How? Because it's writing for all x, dog of x implies has tail of x. So this means if x is a dog, this will imply x has tail. So this basically object is your dog, x is the instance of dog, implies that x is basically having a tail. So this is the formal representation or the mathematical logic representation, or otherwise you can say it's a symbolic representation of this sentence. So for all this word for all x. So for this word also we have a symbol actually. So that symbol is basically a V, and then on that V we place a striking line. So basically that V is striked off. So that so it's basically like a V, and then you have a line which is cutting that V. Basically, it's, I'm not able to draw that on the chat box, but you can see here it's not V minus, it's not V minus, it's V and a line cutting that V, okay, from between. So that is basically the symbol for all. So this is the symbol for all, okay. So that symbol we place over here, but I was not able to draw, so I have written it like this for all x, okay. So in the later slides I will tell you what is the exact symbol, right? So now I have represented this all dogs have tail by this symbolic representation, fine. Now from these two facts, the first fact is Lucy is a dog, the second fact is all dogs have tail, can I derive, or you can say infer something? Yeah, Yeah, Nitin has written it correctly, right? So please see the chat box here, students. The chat box, on the chat box, whatever Nitin has typed, that is the correct symbol for all x. Yeah, this is the symbol for all x. I don't know, I was not able to type that one, but you can see that from the chat box. So Nitin, you have copy pasted it from somewhere, or you were able to draw it from the keyboard itself? Copied. Yeah, yeah, yeah. I think we can copy it from somewhere. Then I we can then it can be possible, right? So that is the symbol which Nitin has drawn. That is the symbol for all x, right? Correct. So now you have two facts. Lucy is a dog, and all dogs have tail, right? So can you derive that whether Lucy has a tail or not? You want to answer this question: Lucy has a tail or not? So you have two facts: Lucy is a dog and all dogs have tail. So can you derive the fact that Lucy has tail? So what you can do is basically from these two facts, yes, you can derive from these two facts that Lucy has a tail. How? Basically, Lucy is a dog, right? And it is written that for all x, dog x implies has tail x. So if you replace in place of x, if you write Lucy, so in place of x, if you write Lucy, then it will be able to derive this has tail Lucy, right? So that means has tail Lucy means Lucy has a tail. Fine. So this is called as inferential knowledge, basically. Fine. This is called as inferential knowledge. You can infer something from the existing facts. This is called as inferential knowledge. So this is how you represent the facts in terms of internal symbols, and basically you can reason. You can reason using the set of facts available to you in order to derive new facts. So this kind of knowledge, which I have just given an example, this is basically using inference mechanism that you are inferring new facts. So this is called as inferential knowledge. Fine. So basically, whatever I just explained you, that you can have an internal representation for every fact, right? So that internal representation could be a mathematical logic representation or a predicate logic representation. So basically, whenever you have a fact, you can have an internal representation of the fact in your own way, basically how you want to represent that fact. So that's called as internal representation. And through some reasoning, you can basically change the internal representations into some other representation, and that would be representing your final fact, which you want to derive, right? So for example, here you have basically got two internal representations. The two internal representations are dog Lucy, and the other representation is for all x, dog x implies has tail x, right? From these two internal representations, you have done some reasoning on these two internal representations, and you got the answer has tail Lucy. So basically, through reasoning, you have basically changed the internal representation, and you got the internal representation has tail Lucy. So this is another internal representation. Fine. And each of these internal representations has a corresponding English generated sentence. Fine. So this is what is represented over here, that you have facts. Fine. And you have the internal representations, and through some reasoning, you can change the internal representations to the final facts which you want, basically, and they will be able to represent in the English format. So some English, through English generation capabilities and through the English understanding, you will be able to represent them, each of these internal representations, in the English language also. But you can change the internal representations for deriving new facts out of the existing facts. So this is just the mapping between facts and representations. But if you see the more formal diagram, this is the more formal diagram to tell you how do you reason. So basically, how do you reason it? Just see, there are some initial facts, right? So there are some initial facts, and you generate the internal representation of those initial facts. And so this process of converting the initial facts into their internal representation, that is called as forward representation mapping. Okay, forward representation mapping is basically when you are mapping from initial facts to their internal representation. That's called as forward representation mapping. Fine. And then so you got the internal representation of your facts. So in that example, for example, you got the internal representation of Lucy is a dog as dog Lucy, and for the other sentence you got it as for all x, then dog x implies has tail x, right? So this is the internal representation of your initial facts. Now, through some desired real world reasoning, you see the dotted arrow, just see the dotted arrow over there. Through the desired real world reasoning, you are able to achieve the final facts. I mean, what you do is through operating the program or through some operation, you convert the internal representation of initial facts into the internal representation of final facts. So that's how we have done. Just see here. So just see here, students. If you see here, you have internal representation of dog Lucy, and the other internal representation is for all x, dog x implies has tail x, right? Now, from this, you apply some reasoning and you apply some operation on these facts, and you get the internal representation. That means the another internal representation has tail Lucy, and this is the internal representation of the final fact. So from this, you can generate the final fact as Lucy has a tail. So that is done. Basically, if you see this diagram, first of all, initial facts are converted into their internal representations to the forward representation mapping. Then you operate the program and do some reasoning and get the internal representation of final facts. And then through a backward representation mapping, through a backward representation mapping, you are able to achieve the final facts. So backward representation mapping means internal representation to the facts. Forward means from facts to internal representation. Backward representation means from internal representation to the facts. Fine. So from this internal representation of final facts, you reach the final facts, and that's how you are able to basically derive new facts from the existing facts. Fine. So this is basically an example of how do you you infer new facts from the existing facts using the knowledge representation techniques. So this is on a broader scale. Then we will also study some different forms of knowledge representation techniques. Okay. So a good system for knowledge representation would actually have the property that it will have a well-defined syntax, semantics, and it will have a capability to express complex sentences. Right? So it will have a capability to express very difficult sentences also. So you have four properties of a good knowledge representation technique. So those four properties are representational adequacy, inferential efficiency, and acquisitional efficiency. So basically, these we will just go through them one by one. They are easy concepts only. If you see here, there are four properties of a knowledge representation technique. Representational adequacy means that the knowledge representation technique should be having the ability to represent all kinds of knowledge. Okay, so if a knowledge representation technique can represent all kinds of knowledge, then it is a having a feature of representational adequacy. So here, one thing I would like to tell you, students, here is that there are different kinds of knowledge actually. Okay, so we will study in the later slides that what are the different kinds of knowledge. So there are different kinds of knowledge, right? You have relational knowledge, you have inferential knowledge, you have inheritable knowledge, you have procedural knowledge. So basically, different kinds of knowledge are there. Fine. For example, the example which I was giving you, where you were inferring a new fact from the existing set of facts, that was an example of inferential knowledge. Okay. So like this, you have different kinds of knowledge. We will study them. So if your technique can represent all different kinds of knowledge, then it is said to have representational adequacy. Fine. Then inferential adequacy means so this kind of inferential adequacy means it can basically your knowledge representation technique can represent the knowledge in such a way that you can derive new knowledge basically from the old knowledge. So it has the capability to manipulate your representation structure in such a way to derive new structure corresponding to new knowledge. For example, in that example which I was giving, your knowledge representation was such that basically you were representing the knowledge in the mathematical logic format, right? In the predicate logic format. So that was having this capability. It was having inferential adequacy because it was able to manipulate both the sentences in predicate logic, and it was able to give you another sentence in predicate logic. So what was that sentence? Has tail Lucy, right? So has tail Lucy was the sentence which you were able to get after manipulating the representational structure of existing two facts. So you were able to derive a new fact. So it was having an inferential adequacy basically. That is the meaning. Then inferential efficiency, it is the ability to incorporate additional information into the knowledge structure so as to move the search in the most promising direction. So basically, this means that your knowledge representation technique should be able to incorporate the domain knowledge, some additional information. So if your knowledge representation technique is able to incorporate some additional information related to the domain of the problem into your searching, so it will be able to basically represent it in a best format, and it can basically search in the most promising direction. So basically, this inferential efficiency means the knowledge representation technique should be able to incorporate the domain knowledge, additional domain knowledge about the problem into the knowledge representation, so that you can basically move the search in the most promising direction. Because if you want to do a good search in your, or if you want to find out a good solution, always you need the domain knowledge, right? So, for example, if you are taking the example of that dog, for example, let us see this example only. So in this case, you know that Lucy is a dog and all dogs have tail. So even if you don't have this sentence, all dogs have tail with you, right? Suppose you have only this sentence, Lucy is a dog. And the question is, has Lucy got a tail? So, whether your knowledge representation structure can actually infer the default inferences from the given information. So, that is basically the incorporation of domain knowledge. Okay. So domain knowledge means, can it infer something which is basically the domain, or you can say the default information available to you. So the default information or the existing fact is that all dogs have tail, right? So even if you don't specify this explicitly, from the domain of the problem, can it basically represent the knowledge in such a way that it can get some additional information? So if it gets additional information that all dogs have tail, then in that case it can infer that Lucy also has a tail without this specifying explicitly this sentence, right? So if it is able to do this, then it is basically having the inferential efficiency also. So how is inferential efficiency? Okay, so Nitin is asking question, how is inferential efficiency and adequacy different? So adequacy and inferential efficiency, let us go back to that slide. You have a class also, students, I think. Yeah, just 1 minute. So inferential adequacy and inferential efficiency. Efficiency means that you are able to incorporate the additional default information into the knowledge representation, right? Inferential adequacy means you are able to manipulate the existing information in such a way to derive new information. So you have your facts with you. You see here, you have dog Lucy and you have another fact, for all x, dog x has Lucy, dog x has tail x, right? So if from these two facts, can you derive the other new fact? If you are able to derive a new fact, that is inferential adequacy. So how efficient it is for combining the two facts to derive a third fact. So that is inferential adequacy. Efficiency means you are able to infer new facts. I mean the default information or the domain knowledge. Can it infer the domain knowledge by itself? That is inferential efficiency. Okay. Fine, Nitin. Okay, so we are, the last point is remaining. We'll continue it in the next class. Fine. We'll continue it in the next class because already time is over. Divya, can you take the attendance? Done. Okay, thank you, Divya. Fine, students. So we'll meet tomorrow and we'll continue with this. Tomorrow, 2 o'clock. Fine? Thank you, students. Yeah, please mail the attendance, Divya. Thank you, all of you. Yeah, thank you.